Yeah, all right. So let us start the class. So I think my screen is visible to you and my voice is also audible.
Yes, sir.
Okay. So in the last lecture, we saw the effect of scaling the VDD, and also we saw the effect of scaling the device dimensions on the delay and other performance parameters, for example, power dissipation. So we saw how these two things affect the circuit performance. Okay, and then in the last class itself, we saw how TPHL and TPLH also change with the device dimensions. Okay, and then the how the delay changes. Okay. Then we arrived at this question, that is how to derive the optimum size of your devices in a gate. Okay. So let us try to size, or maybe try to define the size of the gate. So when I say size of the gate, so that means obviously the sizes of the devices which are inside the gate, right? So I want to size the devices which are inside the gate. So this analysis will be done for a CMOS inverter. That is, we will try to find out the size of CMOS inverter in a chain. In fact, there will be a series of inverter which will be attached in a chain, and we'll try to size those inverters, find the size of those inverters. And the same analysis can be applied to any other logic gate, right? Not just inverter. So this will not be limited to just inverter, but it can be applicable to all other digital logic gates or logic functions. Okay. Now let us define first of all this sizing ratio beta. Okay. So let us say that the sizing ratio beta. Okay. So earlier we said sizing ratio is S, or scaling factor. Now let us say this beta is W P by Wn, or W by L of P divided by W by L of N, right? So for a given process technology, L is same. So we say WP by Wn is beta. And we also assume that the width of PMOS is twice the width of NMOS. That is, PMOS is twice bigger than the NMOS, so as to have same pull up and pull down currents. Right? So pull up and pull down currents are so same. Okay? That is only possible when the resistance of pull up and pull down network are same. That is, our equivalent resistance of NMOS should be equal to equivalent resistance of PMOS. So that is why I keep W of PMOS as twice bigger than W of NMOS. So this will also allow me to have equal TPLH and TPHL. That is, low to high and high to L delays will also be same, so that my VTC will be symmetrical. Okay. Now, if VTC is symmetrical, then obviously I have an advantage of having high noise margin. So high noise margins are possible if I have a symmetric VTC. Okay. Now, yeah, and then if the symmetry and noise margin, so if they are not important, then obviously one can speed up the same CMOS inverter by reducing the PMOS width. Yeah, so we understood yesterday that it is not necessary to make this PMOS wider unless we want symmetrical VTC. If we are okay with asymmetrical VTC, obviously the circuit will have then lower noise margin. So one can reduce the PMOS width so that the speed of the inverter can be more. Okay. Now, therefore, we arrived at a conclusion yesterday that a transistor ratio, that is an optimum transistor ratio, is required, which optimizes the propagation delay of the inverter. So we had tried to find out this point, that is optimum ratio of my WP and WN, that is PMOS and NMOS, and we commented that it should be somewhere around 2.4. Okay, if I want to have symmetrical VTC. Okay. However, the delay can be further reduced. I mean, at this point, the delay seems to be smaller than what it is at this point. So, but yes, at this point, you will not find symmetrical VTC. So, in the cases where the delay is more important, one can use sizing of 1.9. That is, WP is 1.9 times bigger than WN. Similarly, VTC symmetrical VTC is important, that is noise margins are important, then one can keep the WP of PMOS, so that should be somewhere around 2.4 times the width of NMOS. So this is what we commented yesterday. Okay. Now let us say we have a chain of inverters like this, and we are supposed to find out the sizes of each inverter in the chain, right? So we have, let's say, 3 inverters, 1, 2, 3. So we want to find out the sizes of all these 3 inverters, and what we are given is, we are given only the load capacitance, that is the total capacitance which is appearing at the output, and we are also given the input gate capacitance of inverter number 1, that is CG1 is also given to me, right? So 2 things are given, CG1 and CL, and based on using CG1 and CL, I have to find out the sizes of all these 3 inverters, right? So we'll also admit here that CL1, okay, so CL1 is appearing over here at this point, right? So CL1, so this CL1, let me write CL1. So this CL1 is the load capacitance of the first gate. So this is my first gate. So CL1, which is appearing here, this is the load capacitance of the first gate. Now the CL1, the contribution of CL1, so that will have a contribution from the drain diffusion capacitances of this inverter and the gate capacitance of inverter number 2, and also some wire capacitance. So I can write the CL1 as CDP1, that is the diffusion capacitance, drain diffusion capacitance of PMOS plus drain diffusion capacitance of NMOS of inverter number 1 plus the gate capacitances of this inverter, second inverter. So gate capacitance of PMOS of 2, gate capacitance of NMOS of 2 plus the wire capacitance. So this is my total CL1. So similarly, I can find out CL2 also, and then also CL. CL is already given, so I may have then a relationship between CL, CL1, CL2, and also CG1. So that relation we have to find out. Okay. Now, when beta, that is sizing ratio of WP by WN, is applied, okay, so all other transistor parameters also scale by the same factor. So we understood earlier yesterday that when you increase W, then the resistance, of course, it comes down, but capacitance also goes up, right? So when you apply beta, that is equal to WP by WN. So that means the drain diffusion capacitance of my PMOS 1, so that goes up. Okay, so CDP1, so I have a relation now, that is the drain diffusion capacitance of PMOS of inverter 1, so that becomes equal to beta times the drain diffusion capacitance of NMOS of inverter 1, right? So this is an important relation to know here. That is, when you apply a sizing factor of beta, that is when you scale up the PMOS, then the capacitance of PMOS becomes beta times greater than the capacitance of NMOS. Okay. So similarly, the gate capacitance of PMOS of inverter number 2, that is this inverter, so that also scales up by a factor of beta. So CGP2 now becomes beta times CGN2. Okay. So now let us put these 2 things here in load capacitance equation CL1. So CL1 is now modified, and CL1 becomes 1 plus beta CDN1 plus CGN2 plus CW. Okay. Now using this CL1 here, one can find out the propagation delay, okay, by using the same old formula, that is the average propagation delay is given by 0.69 multiplied by CL multiplied by equivalent resistance of resistance of NMOS and PMOS divided by 2, right? So CL, one can put CL as CL1, and so that we have now the delay of this kind, right? So delay we find now, that is TP from this equation, CL1 we use from here, okay, and R equivalent N and P, so that also we utilize, and we will also notice that because of this beta factor, this R equivalent P, so this R equivalent P, that is PMOS, so that reduces by a factor of beta. So I bring it here also, that is R equivalent P, I modify from here, so it becomes R equivalent P by beta, right? So beta is the scaling factor. Okay. So the propagation delay at this point now is this much. Okay, so now we have to apply the same propagation delay concept which we saw here to this entire chain to find out the total delay at the output.
Sir,
yeah, please.
Sir, can you explain what is CW here?
CWL.
Yes, sir.
CW or CWL?
Sir, CW.
Yeah, CW is wire capacitance. So that is the wire which is appearing here between 1 and 2 or maybe 2 and 3. So this is wire capacitance. So wire capacitance also we had calculated. Maybe I think in the last two lectures we were talking about the wire capacitance.
Yes, sir.
So how to calculate by using parallel plate model and difference field capacitance model. The same wire capacitance appears over here, CW. Okay.
Okay, sir. Thank you.
Now the same propagation delay equation for this point can be applied to all these points. In fact, the total propagation delay you will see will be equal to the propagation delay at each point. Yeah, that is propagation delay at this point plus this point plus this point will be equal to the total propagation delay. So we have to apply this to this inverter chain, and then we'll try to find out the sizes of these inverters. Okay. So now let us modify this equation once again. So this equation is now modified here. Okay. So instead of saying R equivalent P and N over here, okay, so we bring this R equivalent N outside and we introduce here R here. So R is R equivalent P by R equivalent N, right? So here earlier there was R equivalent P here. Okay, so we bring out this R equivalent N here. So this becomes R. So R is R equivalent P by R equivalent N. Okay. So this equation is modified propagation delay equation by this equation. Okay. Now to find out the optimum value of beta from this equation. Okay. So what we do is that we partially differentiate this equation by beta and then equate this to 0. Okay. And then try to find out beta. So what we do is we partially differentiate, that is we differentiate the delay equation with respect to beta and then equate it to 0 and try to find out beta. So that beta is my optimum beta, that is optimum scaling factor, and that comes out to be equal to R times 1 plus CW by CDN1 plus CGN2. Okay. Now if the wiring capacitance, that is this wiring capacitance, this dominates, okay, that is the total load capacitance also then dominates because of this wiring capacitance. So then one can think of keeping, larger beta values, that is the sizes of the devices in the inverter can be increased because my wiring capacitance is large, so load is more. So one can think about increasing the size of the inverter unless the till that point where the inverter self loads itself, right? So beta can be increased if wiring capacitance is large. But yes, we also understand at the same time that smaller devices yield faster designs, okay, at the expense of but symmetry and noise margin. So this also one has to keep in mind that you are making the device small, then so that is at the expense of the symmetry of the VTC and also the noise margin is affected. Okay. So this is the optimum beta that we got now. So let us remember this equation. In fact, this is equation number 5.26 in your textbook. Okay. Now using this equation 5.26, if somebody asked me to find out the optimum value of beta, so if you remember the wire capacitance we had calculated some time back for a 0.25 micron process and 2.5 volt VDD. Similarly, CDN1 and CGN2 also we had calculated, okay, for the same problem, and also R equivalent P and R equivalent N. So that we use from a table. Okay. So let us go back to that table. I'll show you that table. So this table, if you remember, so where we had the equivalent NMOS resistance at 2.5 VDD, that was 13, and PMOS 31, right? So this one can utilize, and also we had calculated the capacitances, the value of the capacitances. In fact, we had made another table for the value of the capacitances. And so from that table itself, one can, I think it may be here in this presentation itself. Let us find out. Yeah, this one. So here we had calculated all the drain diffusion capacitances and gate diffusion capacitances, gate capacitances. So we'll utilize these values along with the values of equivalent on resistance of PMOS and NMOS. Okay. So once you use this, so beta optimum can be found. So optimum value of beta using this equation can be found by filling in all these parameters which we had already calculated. And one can found that the optimum beta, so that comes out to be, using equation 5.26, it comes out to be somewhere around 1.6. Okay. let me reuse this thing. So the optimum beta comes out to be equal to 1.6. Okay, but when you simulate the same structure, so then we saw that using the simulation, I mean this plot is obtained when simulating this device, not from equation 5.26. This is by simulating the CMOS inverter using SPICE. So when you do this, so you will find that the optimum value of beta, so that can be located either here at this point or maybe here at this point, right? So these 2 points, as we discussed, that if you want delay to be small, so you can use beta of 1.9, okay? And if you want the symmetrical VTC, so your concern is symmetrical VTC also, delay also should be small, and the VTC should also be symmetrical. So then in that case, you can use beta of 2.4. Okay. Now let us apply the same concept to this inverter chain, and we assume that in this inverter chain we are given this CL. CL is given to us, and we are also given the input capacitance of this first stage. Okay, that is CG1 is also given to us. Right, so this is inverter number 1, this is 2, and this is 3. So let us apply this. Okay, so what are we given? We are given CL is given to us, and the problem is to find out the number of stages needed to minimize the delay. That means how many inverter stages are required to minimize the overall delay, total delay present at the output. Okay, and then what are the sizes of those inverters? Yeah, two problems are here. That is number of stages, n we have to find n, and the sizes, that is beta or size, right? So two things we have to find: number of stages required to minimize the delay through the chain, and the sizing of inverter, right? So how do we do this? So for this, so let us assume that we have a reference CMOS inverter. So this, for example, this could be used as a reference CMOS inverter where the width of PMOS, so that is twice the width of NMOS, right? So we will use this as a reference CMOS inverter. Okay, and yeah, so we'll use this as a reference CMOS inverter. So you will also find, because this PMOS is twice wider than the NMOS, so the capacitance, that is which is appearing here at the input, that is CG in, which is appearing over here, CG in, so that should be equal to C of this, capacitance of this, plus 2 times the capacitance of this, because capacitance of this will go up by a factor of 2, right? So if I say that the capacitance of this NMOS is C unit, okay, so that means capacitance of my PMOS will be 2 times C unit, unit capacitance. So that means total gate capacitance, that is total capacitance at the input here or gate, so that will be equal to 3 times C unit. Now this 3 times C unit, so this will appear as a load to the previous stage, right? So let's say that in fact our problem is that one inverter is driving the other inverter. So we have found now the CG, that is CG of this gate we have found, okay, CG in. So this CG in, this appears as the load to inverter number 1. So this is CG in 2, I'll call, let us say. So CG in 2 is load to inverter number 1. Yeah, so here it is explained, in fact, 2 C unit and 1 C unit we take for iron mass. Okay. Now, so total load capacitance will be now equal to C. Let us again divide the total load capacitance, which is, appearing here. Let us say, let me say that total load capacitance CL. Let's say the load capacitance which is appearing here, let me call it CL for the time being. So the total load capacitance is now divided into 2 parts. One is coming from the extrinsic capacitance, that is extrinsic capacitance which is not associated with this inverter. Okay, so extrinsic means here the capacitance which is not associated with this inverter. So that capacitance extrinsic is coming from the wire capacitance plus the capacitance of the gate of inverter number 2 here, right? So the total load capacitance which this inverter 1 sees is CL, and this CL is divided into two parts, that is intrinsic plus extrinsic. Extrinsic is total wire capacitance plus the capacitance of the gate input capacitance of inverter number 2. Okay. Now intrinsic capacitance, so that also actually appears here itself. Okay. So in fact, CL is the total CL is C intrinsic plus C extrinsic. So C intrinsic is the total contribution from the drain diffusion capacitance of NMOS and PMOS of inverter number 1. Okay. So this C components, that is, one has a contribution from inverter number 1, that is drain diffusion capacitance of NMOS and PMOS, so which we call as C intrinsic, and as a contribution from the capacitance of wire plus capacitance of the gates of inverter number 2, which we call as C extrinsic, right? So C extrinsic is, let me write here, C wire plus CG of 2, okay? And C intrinsic is the drain diffusion capacitance of 1, right? That is CDP also and CDN also of 1. Okay? So if I know my CL over here, so I can find out delay at this point by applying again the same old equation, that is 0.69 RC. C is now CL, that is C intrinsic plus C extrinsic, so delay can be found. Okay. R equivalent is again using the same on resistance of PMOS and NMOS, right? So average value one can take here. Now if we take out this C intrinsic outside here, so this becomes C extrinsic by C intrinsic. Okay. Now we call this part as TP naught. Let us call this part as TP naught. So this total delay equation becomes TP is equal to TP naught into 1 plus C extrinsic by C intrinsic. So TP naught here is called intrinsic delay because it is dependent only on this term, that is only dependent on the intrinsic capacitances, that is the drain diffusion capacitances. Okay. So we call this as intrinsic delay, TP naught. Okay. Now one more important thing you will find here is that this intrinsic delay, that is TP naught, so this is independent of the size of the devices. Okay. So we'll see how later on. Now if you size the MOSFETs, okay, so the resistances and capacitances of the MOSFET also change. So we say that if you increase the size by a factor of S, then the total resistance of a MOSFET reduces by a factor of S, and the capacitance, that is intrinsic capacitance, so this increases by a factor of S, right? So let us replace here in the previous equation, okay, C intrinsic by S times C IREF, right? So this is from the reference inverter, that is intrinsic resistance of the reference, intrinsic capacitance of the reference inverter. So we say C intrinsic scales up by S times that is scaling factor times the capacitance of the reference inverter. Similarly, equivalent capacitance of the inverter, so that reduces by a factor of S. Okay. So we modify our delay equation, and the delay equation now becomes this much. Okay. So we just bring in the R equivalent is now RF by S, and C intrinsic here, so that is now S times C IRF, and we had 1 plus C extrinsic by C intrinsic, so C intrinsic again we replace by SC IRF. So this now modifies and it takes this form, right? So here you will find that TP naught, that is intrinsic delay, so this is independent of sizing of the gate, right? Because TP naught here is only up to this much, only this much, right? It has nothing to do with the size, right? No sizing factor appears over here. So we say that intrinsic delay is independent of the sizing of the gate, and it is determined purely by the technology, process technology, and the inverter layout. And in this equation, if you will notice here that if you make this S infinitely large, right? So if S is infinitely large, so this term becomes 0. So the total delay now becomes equal to the delay of, or an intrinsic delay, right? So intrinsic delay is now the total delay if the sizing factor is infinitely large. But yes, one has to also see that increasing the sizing factor also means that the circuit now also becomes costly, because the layout consumed by or the silicon consumed by the circuit is also very large. Okay. In fact, there is a guideline that if you keep S larger than this ratio, that is C extrinsic by C intrinsic, okay, so this will result into a similar delay, but that delay will come at the cost of extra silicon area. So it is advised not to make S greater than C extrinsic by C IRF, so that the delay, delay improvements are very small if you increase S above this level. But yes, the cost of circuit goes up. Now we again modify the same delay equation here. Now we bring in another factor over here, gamma. Okay, gamma we bring in here, and we say that this gamma is equal to C intrinsic. Gamma is C intrinsic by Cg. Okay. Now C intrinsic is again, maybe let me write over here. Again, let us draw this CMOS inverter over here. Okay. So Cg is appearing over here, this point Cg, and C intrinsic is present over here, C intrinsic, right? So gamma, we say gamma is C intrinsic by Cg. So some sort of fan out, yeah, C intrinsic by Cg. So fan out of first inverter gate, it seems, if the load capacitance is nothing, right? So gamma is, we say C intrinsic by Cg, and in fact gamma is found to be 1, equal to 1, I mean around equal to 1 for most submicron technology. That is ratio of the intrinsic capacitance divided by the total input gate capacitance. So that comes out to be equal to 1 for most of the submicron technologies. Okay. And we also bring in another factor, that is F over here. Okay. So now F is C extrinsic by Cg. Okay. So C extrinsic is my wire plus CL. So that is again appearing over here. So this is also some sort of partial fan out, it seems. Okay. That is, C extrinsic is appearing here, C extrinsic. So C extrinsic has a contribution from wire capacitance and the input gate capacitance of inverter number 2. Okay. So this also seems to be some sort of partial fan out of this gate. That is C extrinsic by Cg is F, okay, or what we call as fan out, that is C out by C in. Okay. So yeah, please.
So this CG will depends on sizing of gate or not?
CG will of course depend. So we had seen earlier.
Previously we have said that the TP node will not get affected by the sizing of gate.
You see that CG we had calculated some time back. So it depends on WN and WP also. Yeah. In fact, this the intrinsic capacitance. So that will have a contribution from drain diffusion capacitance also and gate to drain overlap capacitances also. Right. So gate to drain overlap and also the diffusion capacitance of drain junction. So my intrinsic capacitance will have two contributions, that is gate to drain overlap plus, yeah, so there you mean to say that I said that the C intrinsic has no dependence on the sizing, that is width, right? So that can be noticed, yes, here. Sir. Yeah, here it can be noticed, okay, from this point, or maybe maybe here itself. We say that this is TP naught, right? So this part is TP naught, this much. This is TP naught, that is intrinsic delay. So now this TP naught does not have sizing, right? So S is not here, but S is present over here. So that is how we say, actually it will be obviously dependent, but yes, in the context of this equation, we say that this intrinsic delay, which is given by TP naught, so it does not have S over here, right? So of course S will depend, yeah, I mean this delay will depend on S, but here in the context of this equation, it seems that S is not present here in this TP naught. So that is why we say that it is independent of the sizing of gate. Yeah, TP naught is because only up to this much, right? So it is independent of sizing of gate. Yeah, but yes, intrinsic capacitances and all those capacitance are dependent on the width of the MOSFETs, as we had seen earlier also in this table, right? So all capacitances are almost dependent on W. Yeah, you see here also, this one also has area component, this one also. Yeah. So one cannot say that any of the capacitance do not depend on W. All capacitances depend on W. Yeah. But in the context of this equation, one can say that, okay, so we have defined now TP naught as the intrinsic delay, and that intrinsic delay has no contribution from, I mean, it seems it does not have any contribution. So that is how we say that, the TP naught especially, which is given by this relation. So this has no contribution from the MOSFET sizes. Okay. So next is that we apply the same thing now this to the inverter chain, right? So again, I bring you back to the same problem here. So we have now, let's say, n number of inverters. We don't know how many, what should be the value of n, how many number of inverters are required to have an optimum delay through this chain. So we have to find this n, okay, and we also have to find the optimum delay. Okay. So the total delay of this chain can be given by, adding the delay of each stage. So delay at this point and delay at this point and maybe delay at this point. We add up all these delays, we can find out the total delay through this stage. Okay, and this one stage delay, that is TP1, for example, could be given by using this relation. Yeah, this one. Okay. So let us apply the same equation here to this circuit. So if you apply this, that is TP is TP1 plus TP2 all. So that means my delay equation can be modified TP to include the contribution of each stage. So I can modify this TP. So now this TP becomes equal to TP naught summation. This is J, not I. So I'll write J. J is 1 to N, 1 plus CG in J plus 1 by gamma CG in J. Right. So now this we will apply to this chain of inverter. Yeah, this can be arrived at by looking at this one. With CG in n plus 1 is equal to CL. Right? CG in n plus 1 means, so n is over here. So CG in n plus 1, that means that will be equal to the input capacitance which is present here if some inverter was present. But there is no inverter present here after n. So we'll say CG in n plus 1 is equal to CL. And right, and CG1 is given to us. Okay. So that means we have total n minus 1 capacitances which are unknown. So only the capacitance which are known to us are CG1 and CL. Right. Rest of the capacitances, that is capacitance at this point, CG2, CG3, and similarly CGN. So all these are unknown to us. Right. So we have, that means this delay equation has n minus 1 unknowns, and those n minus 1 unknowns are CG2 to CGN. Right. Only CG1 and CGL we know, or CG1 or CGN plus 1 we know. So these n minus 1 unknowns we have to find out. Right. Now how to find them? So for finding them, we say that minimum delay can be found by finding n minus 1 partial derivatives and equating them to 0. Okay. So minimum delay can be found by finding n minus 1 partial derivatives. Okay. So that is in this equation, if you differentiate this with respect to CGJ, right, that is n minus 1, J is 1 to n. Okay. J will be 1 to n. So n minus 1 partial derivatives of this TP, that is delay equation, if you find, and then equate those n minus 1 derivatives to 0, you will find relationship between the capacitances, the gate capacitances, for example this one, right? So if you do this, then you will find a relation between the gate capacitances, and that relation will be somewhat like this, that is CGJ plus 1 divided by CGJ is equal to CGJ divided by CGJ minus 1. So this you will find, and this will be for J is equal to 2 to n, because J is equal to 1, we know how much is the capacitance. J is equal to n plus 1, also we know how much is the capacitance. Right? So n minus 1 unknowns can be found. So for example, if I put J is equal to 2 here in this equation, so J is equal to 2 gives me a relationship between CG3, 2 and 1. Right? So if I put J is equal to 2 here, I get a relationship between CG3, 2 and 1. Similarly, if I put J is equal to 3 over here in this equation, I get a relationship between CG4, 3 and 2. Similarly, if I put J is equal to 5 here, so I get a relationship between CG5, 4 and 3. Yeah. So that means I can get the relationship between the gate capacitances of all MOSFETs. Right. So from here itself, if we try to find out CG2, so CG2 will be equal to square root of CG1 and CG3 from this equation, right? CG2 will be equal to square root of CG1 and CG3. So in fact, this can be generalized again by saying Cgj is equal to now Cgj minus 1 multiplied by Cgj plus 1, square root of this. Yeah, just from here, looking at this equation, that is Cg2 is square root of Cg1 and Cg3. So this can be extended to find out a generalized term for capacitance. That is, if I want to find out the capacitance of some stage, that is J is equal to 2, right? So I'll simply replace J by 2 here. So Cg2, for example, here will become Cg2 will be Cg1 multiplied by Cg3 because J is 2. Yeah? So this we will get. Now, looking at this equation, I have 3 important observations here, right? So these observations we will utilize now in deciding the sizing of these inverters. Right? So first, please go somebody. So first observation from this equation is that this means that each inverter is sized up by the same factor F with respect to the preceding gate, right? So one has to notice this point, that is each inverter will be sized up by the same factor F with respect to the preceding gate, and each stage will have the same effective fan out, that is C out by C in, right? So each stage will have the same effective fan out. In fact, the total effective fan out of this chain, that is CL by CG1, is the total effective fan out. So this total effective fan out will be distributed across all these points in the stage. I mean, each stage will be having a distribution of this total CL by CG1. Right? And also each stage will have same delay, right? So these 3 important points one has to remember, and based on these 3 important points, one can now find out the effective fan out of the each stage as F, right? So F is now the effective fan out of each stage, and this can be given by this relation, that is a capital F, that is effective fan out of each stage. Okay, so this will be related to the sizing factor of each gate. So F, small f, is now the sizing factor of each gate. So small f, that is sizing factor of each gate, is now related to the fan out of total fan out of the inverter chain. Okay, so you have nth square is nth root of f. So this is actually now the sizing factor of my each gate in the chain, and total path delay through the chain. Okay, so that can be modified if I put f as nth root of f in this equation, the previous. So if I put f here as nth root of f, so this equation can be modified now, the delay equation. So delay equation is now modified, and now it looks like this, right? It is NTP now. In fact, n we bring it because we are adding the delay of all those stages, and there are n stages, so we bring this n also into picture over here. So total delay will be now given by this equation. Yeah. Now total delay we found. So total delay is given by this equation. Now to find out the optimum number of stages, that is this n. Okay. So to find out this optimum number of stages n, so this can be found by differentiating the delay equation, that is this delay equation, by number of stages. That is, you do del Tp by del n. Okay, that is dTp by dn you find out, and then equate that dTp by dn to 0. Okay. And then if you do that, you will find a relationship between the number of stages and the total fan out. Okay. That is, the optimum number of stages now becomes equal to n, and n is equal to natural logarithm of the total fan out. Okay. So now let us apply the same concept, that is, we found that this optimum number of stages is n, and the total delay through the chain is this much. So now let us apply this to this inverter chain. Okay. So I have, let us say, a chain of inverter, and CL is given to me. CL is 8 times C1. Right? C1 is appearing at this point, which is the gate capacitance of inverter number 1. Let us say inverter number 1, 2, and 3. Okay. So these are the given thing, that is load capacitance is given to me. So relationship between load capacitance and the capacitance of the first inverter, input gate capacitance of first inverter. Now the problem is to find the optimum sizes of all the inverters. Okay. So there are 3 only inverters in this chain. We have to find out the optimum sizes of all the inverters in this chain, so that the delay is minimum. Okay. So simply we will utilize this formula, that is N is ln F. Okay, and also we'll use this formula, that is F is square root of NF, that is sizing factor is square root of sorry, not square root, nth root of F. Okay, so we'll use these two formulas. Okay, and if I use this formula, that is F is nth root of F, and F is CL by C1. Yeah, capital F, that is total F is CL by C1, that is equal to 8, is already given to me here. Okay, and F is small f, that is sizing factor, is equal to nth root, n is number of stages, that is 3. So small f, that is sizing factor, comes out to be equal to 2. Okay, now because this CL by C1, that is total fan out of this inverter chain, so that has to be evenly distributed along these 3 stages. So the sizing factor of each gate, okay, so that can be sized like this way, that is first inverter will have a size of, let's say, 1, second will be F, third will be F square. Similarly, if I have another inverter, fourth one, so the size will be F cube, F3, and then F4, and then F5, and so on. So that way one can think about sizing a inverter chain. Not just inverter chain, in fact the same concept can be applied to any logic gate chain, not just inverter gate. Okay, now let us try to extend the same concept for designing a buffer, right? So let us say I have a buffer over here and I want to find out now the sizes of all these inverters in the buffer. Okay, so again we will utilize the same formulas. Maybe you can write this formula, these two formulas, that is N is ln F. Okay, please write them. N is ln F, okay, and Tp is given by this one, NTP naught 1 plus nth root of F by gamma. Gamma is 1. And also write down this formula, that is small f, that is sizing factor, is equal to nth root of F. F is the total effective fan out of the inverter chain, and n is the number of stages. So write down these 3 formulas, number 1 here, then number 2 this one for finding out the total delay, and number 3 this one, that is optimum number of stages, right? So we'll utilize these 3 formulas to find out the sizes of these inverters in the buffer. Yeah, so this is a buffer design, let us say. So let us try to size the inverters. Okay, so can somebody tell what would be the size of this inverter by using this formula? And also consider TP naught is equal to 1, and then we have to also find delay. Yeah, 2 things we have to do: sizing the inverter and finding the delay. And consider TP naught is equal to 1. So 3 equations I have told you to write. One is for propagation delay, other is for finding the optimum number of stages, and the third one is for finding out the size, that is F is nth root of F. Okay, so this one is simple, I think. F is here 64, capital F is 64, okay, and N is 1, right? So small f is how much? Can somebody tell?
8, sir. 8.
Right.
60.
No, not, yeah, 64 it will be only. Yeah, so this
Yes,
will
sir.
be 64. N is 1 here. N is 1. So this becomes 64 only. Okay. So if you have 2 here, then it will be 8. But N means 1, so that means no square root. So this is 64. Okay. What about these two? Let me write here 64. And what about delay? Yeah, calculate delay also. Tell me what is delay also for this one, considering TP naught as 1. Yeah, how much is the delay?
65, sir.
How much?
65.
Yeah, 65. Correct. 65 picoseconds or nanoseconds? Okay, let us say 65 only. Okay. Now what about these two gates? Second. So for sizing these two, we'll have to remember this pattern. That is, we have to size it this way, because this load capacitance total fan out has to be evenly distributed. So for this, one has to size it this way: 1 F, F square, F cube, F4. Right. So first is 1, second is F, third is F square. So that way one has to size. So what are the sizes of these two, and then these 3 also?
1 and 8, sir.
8 and 64.
Let us see. F is 8. Okay, so this is 8 of obviously this is 1 and 8, that means. Okay. So in fact these numbers are given here, you can verify. So the delay will be now 18 and F is 8, right? So that means this has a size of 8. Similarly, for the third one, F is 4 here, so that means this will be 4 and this will be square of 4, 16. The size is 16. Similarly, for this one, this is 2.8, so this becomes 2.8, this becomes 2.8, square of 2.8, and then similarly cube of 2.8, right? So this becomes 22.6. Okay, and the delay you can find out from the same equation as you found out 65 for the first buffer. So second buffer you can find out delay is 18 and then 15, and then last one it's 15.3. Okay. So that way one can find out the sizes of these inverters, or maybe sizes of any gate in the chain, and also the number of stages, and also the optimum delay. Yeah, so all these three things can be found for any logic gate, and not just the CMOS inverter or CMOS inverter chain. Now let us also talk about this power dissipation in CMOS circuits. Okay, so we have two kinds of power dissipation here. So one is called dynamic power dissipation, which is due to the charging and discharging of capacitors. Right? So during the charging and discharging of capacitors, some power is wasted from the source or VDD. So that is called dynamic power dissipation. And the second power dissipation arrives from the short circuit currents. Okay. So it is the short circuit path between the supply rails during switching. Okay. So for a very short moment, you will find that somewhere around the switching threshold, you will find that both the MOSFETs are on or saturated. So during that short instance, my VDD is connected to ground. Okay. So that is called short circuit current. Again, it's a source of power dissipation. Then also leakages can be there, that is leakages through the parasitic diodes and also the parasitic transistors can be present in my CMOS circuit. For example, dynamic power dissipation. So power is consumed, for example, here for charging this node. Okay. And now this dynamic power dissipation depends upon the frequency of transition. Okay. So the total dynamic power dissipation is given by this term, that is CL VDD square F. Now, if we want to bring this dynamic power dissipation down, so one can think about either reducing CL or reducing the supply voltage or reducing the frequency of transitions. Now, this dynamic power consumption is, so these three things can be reduced to reduce the dynamic power dissipation. Now, short circuit currents, as I said, that during when V in is equal to Vm, that is maybe at this point, you will find that both these transistors are on. That is, at the center of VTC or at the switching threshold, we saw that both these two MOSFETs are saturated or on. So I have a direct path between VDD and ground. A short circuit current or short circuit path. So that also means that some power is going waste, consumed. Okay. So that is also a source of now power dissipation. Then there could be leakages and power dissipation due to leakages because of drain junction leakages, that is reverse bias drain junctions can also conduct. Okay, so we may have current through the drain bulk junction, and also the current due to sub-threshold region of operation. We don't want this MOSFET to be on while charging via PMOS, but because of sub-threshold region of operation, this MOSFET is also on. So that means again I have a direct path between VDD and ground, because this is somewhat on because of sub-threshold region of operation. Okay. Then so reverse biased diode leakages, so it could be there, that is this drain diffusion junction. So we had earlier also noticed that if you increase the reverse bias across this drain junction, so the depletion region under this also grows up, and then you can find out at very high reverse biases, you may find that the drain and bulk, they are conducting. Right? So a current is possible in the reverse direction, that is from N to P, that is bulk to drain. So that is also possible. So again, it is a source of power dissipation. Then apart from dynamic power consumption, there could be static power consumptions also. That is static when there are no switching events happening in the circuit. So during that time, we say that circuit is in static state, that is no switching event. So in that case also there could be power dissipation. So for example, let's say if the gate of this MOSFET, that is PMOS, is somehow tied to ground, so this is always on, and if you are applying V in as 5 volt to the input of this, so there is no switching event going on, but still since my PMOS gate is somehow tied to this ground, yeah, because of some unknown reason, so I'll have a direct path again between VDD and ground, so current can flow from VDD and ground. So again, a waste of energy or waste of power because of this issue. Now show the rules of power reduction. So what can be the design rules, or what can be the principles that can be utilized for reducing the power? So first principle could be that keep your supply voltage small. Okay. Though we also understand that if the supply voltage goes below a certain level, the circuit becomes slow. Right. So one has to keep that in mind. Then the other thing is design at very design at very low voltages, that is supply voltages. So this is an open question as it is mentioned over here, that is for somewhere around supply voltage of 0.6 and 0.9 volts. So obviously because delay increases, so it's a topic of research. Then the second option would be to reduce the switching activity, that is F, right? So because we saw that dynamic power dissipation is dependent on F, that is the frequency of switching event. So reduce switching activity, the power dissipation can be brought down. Then reduce physical capacitance. So the capacitance, that is drain diffusion capacitance, if you can minimize, so then that means the power dissipation, that is power used to charge these capacitance, so that can also be brought down. So the overall power dissipation can also be brought down. Now I think scaling and all we had already studied, so I'll not go into this again. But yes, let us talk about this International Technology Roadmap for Semiconductor, that is ITRS. So ITRS is a society which gives the roadmap for semiconductor industry. That is, it predicts or it gives the future plans, that is what should be, for example, for future node, for future technology node, what would be the supply voltage, or maybe what would be how many would be the wiring levels, and then how would be the maximum frequency, or maybe maximum power, okay, or maybe the battery power requirements. So all these requirements or guidelines are given by this ITRS, or International Technology Roadmap for Semiconductor. So they predict or they make predictions for these things, that is all process parameters and everything related to an integrated circuit. So they make predictions for maybe 5-6 years they normally predict. So for example, here let us say they have predicted in 1999 that the technology node will be 180 microns. Similarly, in 2014 the technology node may be somewhere around 30 nanometers. Okay. So though yes, today we are in this era, that is 2020, you will find that 35 nanometer, we have microprocessors which are available at 35 nanometer. Okay. So this was a roadmap. So yes, so this is a roadmap, right? So similarly, supply voltages, they predicted that in 99 it will be 1.5 to 1.8 volt, and by 2014 it will be 0.3 to 0.6 volt. Wiring levels, they predicted that in 99 it will be 6 to 7, and by 2014 it will be 10. So yes, by 2020 there are more than 12 or 13 wiring levels, right? Similarly, frequencies, and similarly maximum power and battery power. Yes, all these predictions are given by this important society, ITRS, that is International Technology Roadmap for Semiconductors.
Sir,
Good time हो गया sir.
Yeah, so I think I'm done with this. I'm done with this, everything. So this we had seen. So let us end the class over here. And if you have any questions, then maybe you can put on your questions. Yeah, so if you have any questions, then maybe you can ask. Otherwise, the class is over.
Sir,
Yeah, please.
sir, sir, in the inverter sizing, you have defined the sizing ratio beta is equal to W by L of P upon W by L of N. And sir, in the calculation of switching threshold, sir, we have also saw the factor R, sir. Sir, are those same? Are both of them same, sir?
Yeah, R is R equivalent P by R equivalent N. So on resistance of PMOS and on resistance of NMOS, right? So beta is WP by WL. So of course R depends on W. So you can say that R also has a relationship with beta.
Oh,
Yeah.
okay, sir. Thank you, sir.
Excuse me, sir.
Yeah, please.
Sir, to decrease the delay, we are increasing the width, and at the same time, we are also facing the self-loading effect. So, how to identify at what point we are getting the self-loading effect so that we can keep the W?
So you keep when you make W large, then after some point you will see that self-loading effect come into picture. Right? So again, for knowing what would be the optimum size so that self-loading effect do not come into picture. So for that you will have to know what is the total output load capacitance of that inverter. That is total wire capacitance and then the total gate capacitance of the preceding inverter. So if the total intrinsic capacitance of your inverter, driver inverter, so that is smaller than the total wire capacitance plus total load capacitance. So then we show at that point the inverter is not self-loaded, right? So that is one of the approaches. So one has to know what is the output load capacitance.
Output load capacitance means we are increasing the internal and external.
Yeah, so internal capacitances are increased by increasing the size. So we say
Yes.
that we do not want to increase the size so that the internal capacitance dominate the external capacitance, right? So what is that point? So for that we need to know the external capacitances. So if we know the external
External
capacitance,
capacitance also we are increasing with the width, sir. Gate capacitance is also increasing with the width.
yeah, so gate capacitance is also increasing with the width. So one has to find out. In fact, I had shown you some time back a simulation also where we saw that the self-loading effects were coming into picture after increasing. Maybe I'll show you that slide once again over here. Uh, yeah, so where the delay does not improve too much, I'll show you. Again. So this slide, if you remember, so propagation delay is dependent on obviously this beta. So we see that when we were increasing, in fact VDD dish sizing also you will find similar relation. Yeah, here this one. So at this point here, maybe at when S is 10, so we see that the delay is not improving, right? So here delay was improving, it was increasing, I mean decreasing at a very sharp rate, but around this point 10 to 14, delay was not increasing, reducing, right? So this is the point where we discussed that self-loading effects are coming into picture. So one has to stop increasing the size once you see that delay is not further improving. That way one can find out the optimum size. So maybe you can restrict yourself to sizing at maybe somewhere around this point 4, sizing of 4 or maybe sizing of 6 is also okay. So depending upon how much delay is there, okay. Delay is improving obviously when you increase the size. So after a certain point, that delay improvement is not significant. So we say that at this point, self-loading effects are coming into picture. So one has to identify this point.
Yes, sir.
Yeah, anything else?
Can you show that graph TPHL and TPLH with respect to the sizing beta?
Okay. So let us see that. This one?
Yes, sir.
Okay.
Sir, in this, the mobilities are assumed to be same or different?
The
Because in
mobilities will always be different.
but in earlier cases, for analyzing the CMOS inverter, we assume it to be mobilities are same in case of switching threshold and all those.
Not mobilities are same, resistances are same. So we make the resistances same by increasing the width of the PMOS, so that PMOS becomes faster now because resistance is brought down. Mobility is
So
not changed.
the mobilities are always different
Yeah, always different mobilities.
in our
Whole,
classes.
yeah, whole mobility will always be smaller than the electron mobility. Mobilities are not changed here. Anything else?
Thank you, sir.
Yeah, if you have anything else, then maybe please. Okay, so I think you do not have any questions. So
Sir.
maybe, yeah, please.
Sir, the R that Ankit Singh is talking about in switching threshold equation. Sir, you have told that small r is directly proportional to width of PMOS upon width of NMOS in switching threshold slide, sir.
Okay. Let us see. Small r. In the delay equation, this one, small r.
हाँ सर, एक तो ये है सर, ये
Okay.
आपने यहाँ रेजिस्टेंस के टर्म्स में सर बताया है, और
Okay.
सर जो सर स्विचिंग थ्रेशोल्ड में था सर,
Switching threshold VM.
ये सर, ये सर.
So what was that R, by the way?
Sir, you told that it is directly proportional to the width of PMOS upon width of N.
Yeah, R is always proportional to width of PMOS and NMOS. In fact, R equivalent N also and P also are always proportional. So small r is also proportional to width of PMOS and NMOS. That is true.
So sir, both are same.
I don't know which R you are talking about, but yes, the R which I am seeing, that is R equivalent P by N. So that is obviously dependent on W. In fact, all resistance
That are related to the calculation of the threshold voltage, switching threshold. VM, we are getting this R.
Oh, here, this one, this
Yes
R.
sir, yes sir, yes sir, yes sir.
Talking about this R is same as that beta or not?
No. This R is here. This one is W. Yeah, this is proportional to WP by WN. Yeah, correct. So this is KP times VD sat N by VD sat P by N. So this comes out to be equal to or proportional to WP by WN. R is proportional to WP by WN. In this case, small r.
Yes sir, and sir the R is equals to R equivalent of PMOS upon R equivalent of NMOS.
Yeah, so that is different. So
that is different.
Yeah, those are the resistances. This is not resistance. Yeah, this is the process transconductance multiplied by the saturation voltage, VD sat.
Okay sir. Now sir, the question was sir, like in beta sir,
Okay.
width by length of PMOS divided by width by length of NMOS. सर उसमें सर लेंथ तो कांस्टेंट है, तो सर अगर लेंथ हटा देंगे तो सर बीटा और ये स्मॉल आर सर सेम हो जाएगा फिर.
Beta and small r both will be same, WP by WN, but this small r, so this has a contribution from this KP and KN also, and VD sat P by N also. So this is not exactly equal to WP by WN. Again, it's an approximation.
Okay sir.
It's an approximation, right?
Okay sir. Thank you sir.
Okay. Yeah, so let us end the meeting then.
Excuse me, sir.
Yeah, please.
Sir, in assignment 4, you asked